Hi, and welcome. We're the Circuit Breakers Robotics 11717 from Troy, Michigan, and we'd like to share what we learned about making an ultra-thin drivetrain. We wanted our drivetrain to be extremely thin, fast, and easy to make. Being so thin allows for device design flexibility inside the robot. The less room that's taken up by the drivetrain, the more room for handling the game piece. We also wanted the wheels to be as far in the corners of the robot as possible for stability. We also liked the idea of using only 2 motors so that we could leave 6 free for other devices. To do this, we thought of different drivetrains, and using a Pew matrix, we decided which would be best. The Pew matrix helped us decide based on many factors such as speed, resources, design integration, durability, and more. Using the Pew matrix makes the process much easier and less time-consuming while still considering many possibilities. We decided not to use big wheels such as Mechanism since we went with 2 motors or Rev Grip wheels. Instead, we used Omni and Rev Traction Wheels, which allowed for maneuverability and the thin profile. We placed 2 Omni wheels on either end of each side. This allowed us to turn with less friction on the wheels due to the fact that there are rollers on the wheels. We then put the traction wheels in the middle with no center drop. The Omni wheels were enough to allow the robot to turn, and the lack of center drop means that it will be more stable during shots. To put everything together, we used a Rev Flat Plate on the outer edge and a Rev C Channel on the inside. The purpose of putting the C Channel instead of another flat plate was for structure. If you had a flat plate on both sides, it would bend easier than having a C channel. The C channel also allows us to add other components on the top or bottom. Using a combo of these two also allowed us to keep each side of the drivetrain to be very thin, yet still support either side of the wheel with a bearing. In between the 2 plates, we had to put the wheels on. To do this, we could have used a hex 5mm shaft, a bushing, and a couple of shaft collars. This would have been easier, but would not have achieved the thinness we needed. So instead, we used a 5x9mm bearing and a 5mm hex shaft. There was a problem with this idea though. The 9mm bearing had a 5mm circle center, and the hex shaft was a 5mm hexagon. Since hex shafts are measured flat to flat and not corner to corner, we decided we could get rid of the corners to a specific amount. Unfortunately, we don't have the lathe to do this, so first we tried using a hand drill, and we placed a shaft in it and spun it against a bench grinder. There were many flaws with this, such as it not being safe at all, and the fact that this would become cone-shaped instead of a circle. Our next idea was to use a belt sander and a drill. This had similar results to our previous method, and again was not as safe as we'd like. Our final idea was to use a drill press and a metal file. This was the safest method since everything was held and was not moving all over the place. It also gave us the ability to control the angle, and if we were patient, get a good result. We also wanted to use a single motor for each side in the drivetrain. To do this and drive all 3 wheels with a single motor, we decided on using a chain. We attached 20-tooth sprockets to each of the wheels with a 3D printed spacer, and then ran the chain through all 3 of them. Since there was a lot of slack on the chain, we used idler sprockets, which also gave us the needed wrap on the center wheel to prevent the chain from skipping. These idler sprockets allowed the chain to be tight. For the idler sprocket, we just put a 3D printed sprocket over a 1/4-inch flanged plastic bushing, which was held by a standoff. This allowed for tensioners that would not cause too much friction, and it helped keep the thinness we were going for. We also added tensioner sprockets that aren't mounted to anything but are floating in the chain. This was to prevent the idler sprocket from interfering when we added supports to the rails, but did allow for more play than we'd like. To put everything together, we used small pieces of Rev extrusion and standoffs. This held surprisingly well and was structurally durable. The flat plate towards the back was a bit unsupported though, but since we didn't have any robot contact this year, we left it like it is. One thing we could have improved on is the tensioner. If it didn't float, then there would be less chain lash. Another thing we could have added was another motor for each side, totaling 4 motors instead of 2. This would make our robot much faster than before. We could also make something to support the back part of the flat plate to make it stronger, but since the wheel is so close, it would have to be printed. We could also make a place to add telemetry for more accurate autonomous. In summary, this ended up being pretty successful. We made a very thin drivetrain without too many compromises. Next time we try something like this, we will definitely try to add another motor to make it faster. We will make another video diving into our entire chassis and intake. So be sure to subscribe to our channel. Thanks for watching, and please, if you have any suggestions or comments on how we could improve any of this, we'd love to read your constructive critiques below. After all, we are here to learn.